Okay. Do you have black tea, black coffee,
Okay,
black tea?
okay,
Yeah,
okay.
without sugar. Yeah? I will drink this too, but if you can drink more of that. So yeah, first thing, again, if you are doing experiments, you'll have to do lots of experiments, right? Experiments will be limited to the range of measurements that you make. But why do we modeling means, if you can explain the process mathematically using underlying physics, then you can extrapolate, interpolate, you can, apply a lot. So that's why most, work we try to do modeling along with, might do some experimental validation, but if you can do modeling and explain, then you can take it further. Okay, so let's talk about particle shape. So did any of you use AI to find out why do we use coefficient of variation than standard deviation? No one? Okay, I'll still give more time till lunch, okay? Okay, let's talk about particle shape, okay? So, I briefly talked about particle shape in the last, size lecture, right? Most often, especially in agricultural materials, you will not see a common uniform shaped materials, right? So we always get a distribution, right? So most of the, again, downstream processing or any process, particle shape, in addition to size, shape will also have a larger influence. It could be, particle to particle, surface forces, cohesive forces, adhesive forces. Shape will also have in larger, rate. Again, flow, flow behavior, bulk behavior, porosity, etc. will also be influenced by shape. I'll show you some examples, okay? But, for one of you, if you're just starting PhD, maybe this will be an interesting topic to relate shape with flow behavior of, particles. There are some, work that are published, but still there are not much, understanding developed on the effect of shape on flow, okay? So times, it's the process dependent. Again, this is a mill lactose sample. If you use hammer mill, then the shape will be different than a spray dried, lactose powder. Okay, suppose spray dried often, gets spherical agglomerates, but if you are using hammer mill or other types of milling, you get all, high aspect ratio particles. Okay, in that mix. So again, as we just talked about in the last lecture, is often, size dependent, right? So smaller size might have a larger, uniformity than, large size particles. I'm sorry, it's vice versa. So larger particles may have, sometimes more uniformity than smaller particles. Okay. Again, it's not a blanket rule, but depend on the particle. We talked about the wheat flour example, right? So wheat flour example, smaller particles might be more spherical than a larger size particle. Okay. So almost, again, as said, almost all properties from density to texture and feel, etc. We'll go through some, examples and, measurement methods. So shapes and packing, some shapes might pack more tightly than regular spheres, spherical particle. Do you guys know this candy? Small. I forgot the Indian name. Gems. Yeah, gems. So it's, it's called M&Ms or Skittles in the US, right? M&Ms is common. Okay. Do you know the shape of gems? Usually not balls, right? Elliptical, or it's called spherocylinders, right? So spherocylinders and mostly ellipsoids, okay, they pack more than, a regular, spherical or cylindrical particle. Again, this is a simulated image. You can see when compared with a spherical particle and a cylinder, a spherocylinder will have a better packing. Okay, so most of the time you might see these kind of, gems vending machine, right? I'm not sure if they have in, malls and stuff. You might see those small. You put some coin and you get some gems. Do they have here? No. Yes, right. So you might see this kind of, small spherical bottles where you have, these candies, right? So if you wanted to pack more, mostly, it's in spherocylinder or ellipsoid shape. So with, just a comparison example, with the increase in aspect ratio, might, the porosity will also change. So around, 0.5 aspect ratio, that's very close to an ellipsoid shape, you get, a better packing of the materials, okay? In same example again, with the change in, and again more spherical particle, you will see a higher change or higher, wide, wide or bed porosity than other shapes, okay? On flow, again, if you compare cubes and spherical particle, the cubes will have, a better flow. I'm sorry, spherical particle will have a better flow than, a cube, right? So the spheres, there will not be any corners, right? The chances of interlocking will be low. So the spherical particle will flow uniformly or smoothly when compared with irregular, shape material. Again, this is a, simulated, image. And mostly, if it's plate-like, high aspect ratio, then the flow will be very challenging. Okay, you might have to use some, flow aids to, make them flow. Similar again comparison of different shape, particles. In general, again, round particles will have a better flow or low unconfined yield strength. You all would have heard about unconfined yield strength, right? Anyone? Well, again, we'll talk about that in the flow lecture, but you would have heard definitely during BTech, but you might have forgotten. So that's related to flow. Round particles will have a lower unconfined yield strength. That means their flow will be better, okay, when compared with, a heart-shaped or star-shaped particle. Okay. On rheology, it's a little difficult, relationship. No, good, thanks. It's a complex, it's generally, if it's, more spherical, in general you might see lower viscosity when compared with irregular shaped or, high aspect ratio particles, okay? But again, it's a complex relationship. If you have uniform ideal spherical particle, then viscosity might be lower or easy, it might flow easily than a fiber shaped or other shaped, differently shaped materials, okay? Yeah, there are tons of examples that you can see, but as it just flowed through, the effect of shape on flow is not very well understood. But most of the other parameters, you can see lots of papers published on the effect of shape on their, other process performance, handling behavior, etc. Okay. Okay, so if you are characterizing the shape, in general, try to fix, or characterize into three different, shape parameters, standard shapes like, sphere, circle, etc. We'll go through some of those, shape coefficients, mathematical shape functions, etc. Okay. Can anyone name one shape coefficient that we always calculate? I just talked about it. Okay. Sphericity, okay. What else? Roundness, okay. Roundness is more like a standard shape, right? Sphericity, roundness, etc. Okay. But the same parameters, if you use as aspect ratio, circularity, etc., are kind of, again, shape coefficients. Because their maximum value will be 1. They value from coefficient, right? It's a coefficient, so their values will range from 0 to 1 or 1 and above, depending on how you calculate. Okay. And also we do different characterization like micro scale, very small surface smoothness and porous behavior, or like roundness and angularity, or like spherical, sphericity, circularity, all those things. We do characterize shape based on like micro characteristics, surface characteristics to the large, particle characteristics. Okay. Might see lots of these different shapes. I will not be going into, given some examples here. Okay. You will see when you take any, some are for food and some are for, pharmaceutical solids, but when you take any type of powder, you might see different shapes, right? Needle shapes, very common, right? If you take any type of fibrous material, if you're milling some grains and stuff, most of the fiber materials will be, this kind of, acicular or needle shape, angular. I might not see a lot in, in food powders, but if it's purely crystalline, then you might see some, angular particles. And then crystalline, well defined, like sugar and salt, will have cornered, particles. Then dendritic, mostly it's the crystal forming over crystals. If it's a continuous crystallization, you might see this dendritic shape. Okay. Flaky, right? So when you make soybean, oil, what you do is like you make, flaky particles, right? Flakes after making that. Fibrous, again, thread-like. Aggregates are very common if larger number of small particles combine together and forms into aggregates, right? Irregular shape, very common, any symmetry. Mostly, if you take any small, powder, small particles, then you will see this, irregular, asymmetry in the shape. If you take protein fragments, you will, you might see this kind of irregular shaped a lot, just pure protein fragments. Rounded and irregular shape, thinking of an example, but sometimes, for example, you might remember, a picture maybe or may not be, a wheat flour particle, right? So that had some starch and protein, glued together. So that makes it more rounded, but it's highly irregular in shape. Yeah. Thank you. Thanks. Yeah. Rounded and irregular shape, spherical again, starch granule, right? It's more spherical and globule, uniform shape, right? And based on degree of association, so if you have more number of particles stacked together, if you are having like plate shaped particles stacking together, you might see this lamellar, foliated. If it's thin sheets, you might characterize them as foliated, cemented, druzy, etc. Cemented is like hard agglomerate. So if anyone working on agglomeration of powders, food powders? No? Like for example, coffee powder that instant coffee powder, most often it's agglomerated, right? So you might see this kind of similar, like they add some binder and make it into a little larger granule, those are like cemented. Druzy mostly if it's, crystal particle and if it has some surface, other impurities like dust, or could be some amorphous particles on crystalline solids. Those are attached together. Those are easy to separate. It's called druzy. Okay. And again, based on the degree of association, you can see, primary particles or agglomerates and aggregates. So primary particles, again, if you can make them individual, there is no cohesive and adhesive bonds between those particles. Like for example, if you take, glass beads, they're not, they don't have any cohesive and adhesive force, right? They do have, but very small. But those will be like very primary particles. There's not much, forces on the surface, and agglomerates bound by some weak forces, so it's easy to separate. Okay, right? So those are called agglomerates. Any of you, you all know caking, right? Caking of food powders. Right, if you leave your sugar out, or salt out in your countertop for 5-10 days, it slowly forms into small agglomerates, right? Into small agglomerates. So those are like easy to break, right? If you press with your fingers, it breaks, right? So those are small agglomerates from, caking. Aggregates are more bonded. There will be higher forces between the particles. They are bonded well together. It will be difficult to, break them into primary particles. Okay. Sorry, let me drink some tea. Is that okay if it comes in video? Drinking tea, okay. Okay, so we'll talk about some ratios, okay, that we commonly calculate, okay. Again, no one has used image J, right? No, image J, it's a, image processing software. It's very, you can, easy, it's easy to use, it's free to download. You can, download and, install on your laptop. If you are doing some characterization, it will be, use some images, and I believe you can automate that too. Okay. So some of the extremum ratios like Hayward ratio or the aspect ratio. So we use two major dimensions, either length and breadth or breadth and width, and then calculate the aspect ratio, right? So again, elongation ratio or aspect ratio, chunkiness, flakiness, etc., from either length and thickness and breadth and thickness, etc. Okay. So one of the important thing to make sure to remember is, so elongation, some of the formulas use B over L. Okay. So when you are using any softwares, make sure to know what formula they are using. Okay. Depending on the formula, their values will also change. If you are if they use L over B, then the maximum value will be 1. Okay. But if you are if they are using B over L, then the minimum value will be 1. Okay. So just make sure what type of aspect ratio you will be characterizing when you are using any formula. Okay. Again, sometimes you can calculate the aspect ratio from the best fit ellipse. So again, using the major and the intermediate dimension of the particle. Okay, from the major and intermediate you get the aspect ratio. So as you can see, if you take A over B, usually it's greater than or equal to 1. If it's 1, it's more circular than high aspect ratio. Okay, again, this is the method that image J uses to calculate the aspect ratio of particles. Okay, I'll just quickly go through this. I'm sure you all would have learned about all these aspects, right? Aspect ratio, calculating aspect ratio, circularity. Circularity, again, from the perimeter of the circle that encompasses the particle to the perimeter of the particle. Okay, and then very simple formula to calculate. Same for sphericity too. Mostly a circular and spherical particle will have a circularity or sphericity of 1. If not, again, the values will be low, right? So any example of particle that have a circularity or sphericity of 1? Any agricultural material? What? Be loud, yeah. Green peas, okay. What other example? Mustard seed, okay. Anything else? Soybeans, but they will never be 1, okay. They will be close to 1, above 0.9. So green peas will be a little low, but mustard seed will have better sphericity. Soybeans, okay. So again, typical sphericity is again 0.64 to 1 is common, but if it's more platelets, like fibrous particles, like a fiber, like a bran particle from a wheat milling, then their sphericity will be very low. Okay, we'll do some calculation, okay? Just to get you into the mode of calculation. We didn't do any calculation in the previous lecture, right? I do not know their answer, but you all will have to come up with the same answer, okay? Okay, so show that the circularity of a particle, defined as, perimeter of circle over perimeter of particle, and then, you can, this is a simple derivation of formula, you can, ignore that, okay? But can you calculate the circularity of an equilateral triangle? Okay, do that calculation, okay? So again, circularity formula is perimeter of circle over perimeter of the particle, right? 0.83. Who got the answer? You told? Okay. Anyone else? I don't know the answer, so that's why. If you give the answer, that should be the correct one, right? Okay, calculate, do the next one. Okay. So calculate the circularity of a rectangle with side length ratio of alpha. Okay. So how many if you got 0.83 for B? So, what did you ask about the pharmaceutical thing? Yeah.
Actually, I'm working on micro-inky solution
Oh, okay, okay,
mangiferin, which is extracted from the mango leaf. So
okay,
I have done the micro-encapsulation, so it is a powder form.
okay.
So I want to characterize how it relates. I just want to see
Oh, okay.
characterize all the particle density, ball density,
Oh, yeah, sure, yeah.
safe.
Hmm. Yeah, so you can use all these methods,
Okay.
But, if you have any question, you have my email ID, right?
Yeah.
Okay, just email me, and I'll be happy to.
Okay. And what kind of instrument will I can use?
There are,
This characterization.
for pharmacy, then for size you might want to use a laser diffraction that will give more accurate result. But for shape, you can just use any optical microscope,
Okay.
get the shape, and as said, you can use ImageJ software.
Image,
Yeah,
okay. It's a free software.
free software, free to download. So
Okay, so we can measure the
yeah, shape parameters. Yeah,
okay.
yeah. So you don't have to. Yeah.
I'll try to learn.
Sure, yeah. And again, if you have any questions, you can email me. Yeah. Okay. Any of you got values for both B and C?
So for B, I got 0.77.
Okay. So someone is wrong, right? Okay.
And for C, it's 1.77 joules
Okay. Hopefully, I'll bring you the answers afternoon, maybe. Afternoon, no, I don't have, I'm not teaching, right? Afternoon is lab for you guys, right? It's particle characterization or something. Yeah. I'll bring you the answers tomorrow, okay? But you solved it, right? No. What's that? Question? Sorry. The second one? Okay, I'll bring the answer tomorrow, okay? Okay, so again, I'll skip this one. This is again direct, derivation, equating different volume and, surface. I have the answer too here, but I will show the answer. But do you guys want to calculate? Interested? I had one yes somewhere. Okay, so show the equivalent volume diameter dV of a particle can be, related to the surface area diameter ds by, this relationship. So psi here is the sphericity, right? So psi here again, you know, it's a, you know, surface sphere to surface area of particle. You know, you can get that relationship. Okay. So again, you know the surface area of sphere, and you know the surface area of a, you know, surface area of the particle, and then when you use those two, you get this, you know, relationship. Okay. It's again, you know, a simple and easy derivation. Okay. 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 I'll move on to compactness. And compactness can be defined in many ways. Again, very similar. Like, you know, you take a circumscribed circle and its area, and then calculate the area of the particle. Then you calculate the compactness. So compactness means how close it fits to a circle. Okay. So you can use both. You know, you can calculate using both the inscribed circle and also the circumscribed circle. Okay. So most commonly we use the circumscribed circle, you know, to calculate, you know, the compactness, how close it is, you know, or how close it is to a circle, you know, when it comes to shape. Okay. Again, calculate irregularity of the particle using those areas of inscribed circle and the circumscribed circle. Okay. So again, if it's compact and if it's close to circle, then the, you know, the value will be 1. Okay. So that's the max. Solidity, very, you know, similar concept like, you know, the compactness, but you are, you know, instead of a circle, you are making a convex hull. So you are, you know, you are not using all the, you know, void spaces around the particle. Okay. So you are using a convex hull, you know, making it convex, you know, just touching the protruded edges of the particle. Okay. And then calculating the area of that convex hull and the, you know, area of the particle to calculate the, you know, solidity of the material. Okay. Very similar to compactness, but only difference is compactness we're measuring to a circle. Okay. Again, roundness is how round the corners are. So you calculate the radius of all the corners of the particle and then use those values to get the roundness. Okay. So again, mostly for, you know, we talked about one rounded, you know, uniform particle, right? It's like a wheat flour particle. Okay. So you can get the roundness on those corners, and then, you know, the radius of all the circles that are on the corner, and then get the, you know, roundness of the particle. Okay. Again, there are different formulas. I said, you know, it depends on the equation you use. You know, you might see different formula that are being used for calculating roundness, you know, from the area or from circularity, etc. So when you are writing a paper or writing your thesis, make sure, you know, if you're using calculating roundness, make sure to, you know, mention the formula that you used to calculate the roundness. Okay. You know, different softwares like Malvern, if you're using Malvern software, then they might use a different formula than ImageJ software. Okay. So shape factor, again, you know, I briefly talked about shape factor, right? So surface area shape factor, you know, again, you know, based on the surface area of the particle, volume, etc. So the shape factor will also depend on the shape, right? So if you are calculating for a spherical particle, you know, the shape factor for surface area shape factor will be about, you know, pi, and then for the volume shape factor will be about, you know, close to 0.5, and then for cubes also it differs. Okay, I'll not go into the shape factors yet, but again, this mostly we can use for converting from one size to another size, or from converting one distribution to another distribution. Okay, it's again simple calculation. Okay, if you know the volume of the particle and if you know the particle size, you can calculate the shape factor. Okay, and then you can convert from one shape factor to the another factor. Okay, simple calculation. It's not very, you know, complicated. So, any questions? No. Yeah, go ahead. Yeah. Okay. drowsy, there are many examples. So if you take, you might see instant soup or soup mixes, etc., right? So they are very cohesive, right? But when you are adding to water, they flow well, right? When you are opening the packet, so they add some, flow agents, flow aids, dispersants, etc., right? So those particles, those flow aids and flow, dispersants will be on the surface of the main ingredient like this, it's not attached to it, but will be on the surface. But if you shake it off, it can, come out. So, right. So like mainly, flow agents, flow aids, anti-caking agents. It's very common in powder to powder mixing. So if you're mixing a small particle with a larger sized particle, then you might see lots of, druzy particles. Okay, go ahead. Yeah.
So circularity, compactness and roundness, all these three are giving idea about how flow lead to a circle.
Circularity, you said circularity and compactness, right?
How close a particle to
Yeah, to a circle, yeah.
So can you please give a condition where we can use circularity over compactness and vice versa?
Okay, so circularity again, one thing is, you see circularity again, we are using the perimeter, just the perimeter, okay? So you can have multiple rounded edges or multiple edges on the particle, for example, I'll try to draw, thick, but, for example, if you have a particle like this with more rounded edges like this, okay, so it's not uniform, it's highly irregular on the surface, okay, but it's close to circle, right? Its circularity will be high, okay, but their compactness will not be high, since it's calculated based on the area. So you will have lots of, so white spaces here, right? So their compactness will be different than their circularity, okay? So it depends, might not, it's not the same, but it quantifies close to circle, but you might have different values for different particles.
That's clear that this
Okay.
is different. But still, condition when we can use like we have to use circularity, we can't use compactness.
Not really, there is no, you can use both, you can calculate both, yeah.
What is significant? How to understand?
So as I said, circularity will give this one, okay. Like if it's rough, it can have rougher edges, but it still can be a circle, okay. But compactness is, if it's rougher edge, again their compactness will be, might be different, okay. Where it, applies means, for example, we talked about powder to powder mixing, right? Okay, so if it's circular and if it has lots of, rough edges, you cannot fit smaller particles, you cannot fit lots of smaller particles inside. For example, you are adding, I forgot its name, very common in instant soups, instant, those kind of food mix. They add a dispersant, okay, it's very fine particle, okay. So you can add, I think it's magnesium stearate, if I remember correct, okay. You might have seen in, if you read those labels in instant soups or instant food powders, most of them will have, I believe it's magnesium stearate, okay. Those are very fine particle, if it's circular, but if it has only rough edges, it's uniform, you may not be able to fit lots of, those fine particles inside, okay. Same thing, it can be compact, okay. If it's very compact, then you may not be able to fit lots of particles within their wide spaces, okay. Then you rely more on their cohesive adhesive bonding rather than fitting the particles within the pore space, okay. So that will, again, yeah, circularity, compactness will come into play mostly, when you deal with, agglomeration, powder to powder mixing, adding some ingredients, etc. Okay, is that clear? Little bit? Okay, but we can talk more, okay. So solidity, again, solidity is not close to, more about convex hull, it's how much external void space are, right? This it's a little different than, equating to a circle, okay? Any questions? Okay, so let's talk about fractal dimension. Okay, so fractal dimension, you all know about fractal dimension, right? Fractal characteristics are surface irregularities, right? And mostly we use that for characterizing the roughness of the particle, right? So there are three common methods to get the, fractal dimension. The yardstick method, box method, agglomeration, agglomerate method, etc. Okay. Do you know how first the world atlas was drawn? The atlas, the map, world map. How do they know, how much area or how much, the distance it covers, right? So the first, I think the first method that they used was yardstick method. Okay. So that was used to create atlas or world map. Okay. So getting, using some specific dimension and getting the, distance, okay, and creating the map. Okay. So it gives a measure of ruggedness or the surface outline of the particle. Okay. It's, it can be two-dimensional or three-dimensional, etc., depending on how you are characterizing. Okay. And again, if it's a line, talk briefly about these methods too. Using, if it's a line, then usually the fractal dimension is 1, but if it's very rugged, then it varies from 1 to 2. Okay. So, but we talked about yardstick method, right, to get the world atlas or world map, right. So, what will be one major disadvantage of this yardstick method? So again, and I'm not going into the think about it. Okay. So again, yardstick method, I said, you use some yards, sticks of definite size, and then characterize their surface fractal behavior or surface texture. Okay. So again, you can get, the texture of the material based on if it's rough or smoother, etc. Okay, based on the yardstick. So usually, as we talked about, if it's close to 2, highly irregular, and if it's close to 1, the value, the particle will be very smooth. Okay. So again, coming back to the question, what will be one major disadvantage of using an yardstick? What?
If the particle is too much coarse in nature, we can't use it. For liquid particles,
Maybe, yeah. You can. What is it?
for liquid particles, we can't use.
Still, if you just need a good image, right? 2D or 3D image, so you can use,
For
any.
irregular shape of
What's it?
the particle shape is more irregular.
Okay, don't think from the particle side, think from the other side. So, what will be one major disadvantage? Okay, I will give a clue.
Curves and angles are neglected in this.
Not really. So, very close to answer, but we don't neglect. We still use, calculate them. But very, yeah, go ahead, go ahead.
When we're taking an image that is 2D, so we have to take more than 2-3 images.
It's not a major, you can still measure, That's not the major disadvantage. Yeah, that's one problem, but, what you said is very close, but it's not the exact answer. Okay. Anyone else that you can think of? Just think, not from the particle side, think from the other side, from the yard side, the stick side.
We need to go and keep the sticks.
That you can automate. You all know Python, right? Most of you. So you can just automate, so it's not a big deal. So. Okay, so yardstick, right? So as the image says, the fractal characteristics will depend on the size of the yardstick. So if you change the size of the yardstick, okay, their fractal dimension will also change. For just for this example, using this length of yardstick, right? But if I halfen it, I can cover more surface, right? So again, depends on the method that you are using to characterize. So make sure when you are using an image analysis, make sure you know what type of method that that method or the software is using to get this fractal dimension. Okay. The other common is box counting method. Again, take an image and split them into box sizes. Okay, some definite pixel size, 2 pixels, 5 pixels, etc. Divide them into smaller boxes, and based on the number of boxes that the image has, you get the fractal dimension. Okay, so you get the number of boxes that falls, that particle falls into it, and then get the fractal dimension. Again, very similar, if it's close to 1, again very similar to the yardstick method. If it's close to 1, perfectly smooth. If it's close to smooth, close to 2, it's highly irregular shaped particle. Okay. Again, aggregates, it may not use a lot, but if you are dealing with, if you're working on like blood samples, or smoke particles in air, then you might use this method of aggregates, or using smaller aggregates of particles or granules, again mostly in submicron level, and then use those aggregates and the dimension of those smaller aggregates to get the fractal characteristics of the larger aggregate, large aggregate particle. Okay. Not very common in our field. Okay. Fractal dimension, again surface roughness. So, this one method I did not include. Again, for fractal dimension, you can use Fourier series expansion too, based on the change in surface characteristics. Use some simple Fourier series expansion, and then get the fractal characteristics. Okay. So again, roughness, you can use different. Mostly we use this optical microscopy method. It could be simple optical microscope, scanning electron, etc. Light scattering are very simple to use and easy to measure. But little, if you wanted to have more, in-depth measurement, then surface profilometry will give a better quantification of the roughness of the material. Okay. Atomic force microscope is one common. Again, there are particle profilometers that are very common nowadays. That can get the roughness of the particle. Okay. Anyone used an AFM, atomic force microscope? No. You might be using in your PhD research later on, but it's very expensive process and very time consuming process. But there are other simple profilometer that you can use too. Very commonly used in for example measuring friction, etc. Not measuring friction, but for studying the effect of friction. Tire industry, metal industry, etc. When their surface texture or roughness will change based on the use, right? So they use these kind of profilometer to study their change in roughness, of their material. So statistical measures are very common. Again, fractal dimension we just talked about. That's one common method for calculating roughness. So mean roughness and root mean square roughness. Again, you will need little in-depth measurements, either using atomic force microscope or using some profilometers, or if you have a very good image from scanning electron microscope, you can do that mean roughness and root mean square roughness calculation too. Okay. But why do we have to calculate roughness? How any examples of how it affects the process? Okay, flowability will be definitely, if it's rough, then there will be higher chance of interlocking between the particle, and then they may not flow well. Any other examples of process, process performance?
Angle of repose will be more for rough particles.
No, I'm talking about small particle. Yes, angle of repose will be high for highly irregular particle. Yes. So, for example, if you're using we talked about instant soup powder or instant coffee powder, right? So, do you want the particle to be highly the surface roughness should be high or small or low? Which will be better? Low. Okay. So, you have one more option. Okay. Okay, so increase in roughness, what happens? So it increases the surface area, right? So it increases the surface area, and if you want, again, it could be low or high too, but depending on your end use. If you are talking about instant soup powder or coffee powder, you want a high roughness. So it can absorb more water and dissolve quickly than a smooth powder where it will have less, surface roughness. Okay. So depends again depending on application. So if you are quantifying some of those, these parameters will be useful, like mean roughness, root mean square roughness, etc. will give more understanding about the particle characteristics. Same for pharmaceutical medicines too. If you wanted them to dissolve immediately, then you might want a high surface roughness than a smoother particle. Okay. But again, you'll have to compromise something. If it's highly rougher, then the flow will not be good and uniform. But if it's again, you will have to draw a point where you can compromise all the properties so that you can have a better product. So extreme measures, again, maximum peak height, etc. Within those surface roughness, you can get the peak heights, valley height, etc. This will commonly play a role when you are working on, like, for example, coating of materials or agglomeration of powders. Okay. So this will define, for example, if you are agglomerating milk powders, this will define peak heights, the roughness will define how much binder you need when you are agglomerating. Because if the peak heights roughness are high, then you might need more, it might take more binders, because most of the binders will get into here, and then it may not be available for forming agglomerates. Okay. So when you are working on those coating of, like, even encapsulation, coating, etc., you will have to worry about these extreme measures. Okay. Just one example here, do you know how many different types of wheat we have? I'm not sure in India, at least in the US conditions, there are like 7 different wheat classes. Okay. So they are mostly used for different purposes. For example, if you are someone ate noodles for lunch yesterday, that's you, right? Okay. Yeah, durum wheat, right, for noodles. But for cakes and pancakes, we use soft wheat, right? For bread, we use hard wheat. Okay. Do you know what type of wheat flour used for pizza? Any guess? Hard, soft, or durum? Okay, we cannot use durum, right? It's high protein, so it will be very harder, like noodles. Okay, so in common they use a mix of hard and soft for pizza and most of the products. So just to say, soft wheat particles are softer in texture, right? But when we take a closer look, okay, the soft wheat particles are much rougher than a hard wheat flour particle, but they are still soft with low in protein, but their roughness is completely different. So how does it play a role? This affects the sieving performance or sifting. When you are sieving these particles, hard wheat flour will be easy to sieve, okay, than a soft wheat flour. You can try when how many of you cook when you go home? Some of you, when you make roti, take out of flour, when you sift, it will flow very smoothly. But at the same time, when you take some flour that you use for baking purposes, when you sieve them, it will not flow very easily. It will be very difficult to make them flow. Because again, those roughness and other characteristics influence their. I'll skip this again. Roughness increases porosity. So again, particle shape, almost influences almost all the behavior of the powder. As we said, we can quantify the shapes, quantify their surface roughness, surface characteristics. Again, it gives more understanding about the particle. Okay. One small example again, again, if the particles, you are doing some agglomeration of coffee powders, okay, and sometimes with the change in process, you might see that instead of 1 liter of binder, your process is using like 3 liters of binder. Okay, you may not know why it's happening, but when you take a closer look at the particle, might be the particle surface roughness has changed. That's why it's taking more binders than it should. Okay, then you change the process of milling so that it's not rougher anymore, so that it can do the same process with lower amount of binders. Okay, so again, depending on the process and depending upon what your end goal is, you will have to characterize different shapes and surface characteristics. Okay, again, there's one standard that talks about shape characterization. Again, mostly they talk for powder metallurgy, but it's applied for all the materials. That's it. Some lots of references. I think that's it on the shape. But I think I should have. I didn't include in the presentation here. I've used this roughness for moisture absorption during my PhD work a long time ago. So how particle roughness will influence absorption behavior. If it's highly rough, then it can absorb more liquid on the surface than if it's smoother. Okay. So how it affects, again, you all would have learned about liquid bridging, caking, etc., right? So if it's rougher, then there will be more liquids on the particle that's available for forming liquid bridges between particles that can lead to caking of powders. Okay. So it can give you again, these shape characteristics can give lots of fundamental information that you can use for other purposes. Okay. Any questions? Tired of listening? No, not yet. Okay.
Sir, in our soup and the particle will be less rough, then it can form cake.
It can.
It can form cake.
It can form, usually, soup powders, milk, dairy ingredients, food powders, they cake a lot. So that's why they add some flow aids and, anti-caking agents. So most of them will have some amount of, at least 0.5, 0.2, 0.5% of these, ingredients that prevents from caking. That's why you might have seen, those instant mixes will have a specific packaging with non-absorbent packing. Okay. Any other questions? No questions? Okay, so let's take a couple of maybe 5 minutes break. We'll talk about surface area and porosity maybe. What time is lunch? Do anyone have a schedule? 1:30. Okay. So we'll finish one more lecture. That'll go quick. Okay. About surface area characterization, and I think that's the one we'll talk about next. We'll talk about density tomorrow. Okay, density, and we'll start with flow, powder flow. Okay. You are missing in the morning, right? Were you here? I can see who now, since I'm standing here. I see some attrition, Okay, any questions from the last two lectures?